All right, here we have for class 23 some examples. This is example 1. We did this one in class. The 30 kilogram double pulley shown has a radius of gyration of 0.25 meters. And the small pulley has a radius, the large pulley has a radius of 0.3 meters. Kaboom. And the small has 0.18 meters. The attached cables support this 25 kilogram weight with mass, which we'll call A, and a 10 kilogram mass, which we call B, and it starts from rest, and we want to find the time that it takes for the 25 kilograms to reach 2 meters per second. So some preliminary stuff, we get the mass moment of inertia by taking that mass of the pulley and the radius of gyration which was provided and squaring it. And we get 1.875 kilograms but times meter squared. We know that the end state, that VA2, is going to be 2 meters per second downwards. We can use some basic kinematics to establish what the angular velocity at that second state is going to be, 6.667. And then from that, we can also figure out what the velocity of B at the second state is going to be, and that's just going to be that omega 2 times RB. So we have this. So we can set up that first state. This is the before something happens to it equals after, right? So we have our angular impulse and momentum equation where the counterclockwise is considered positive. And so here's all the angular momentum before. Here is the angular impulse that happens to the system, and here's the angular momentum after that occurs. So I wrote out the equations here on the left-hand side that are possible to happen. Of course, we know that omega and VA and VB1, they're all going to be 0. And then we look at what's here in the impulse side. We have the weight of A times the time, right? That's the impulsive force, but this needs to be angular impulse. So we also need a moment arm, RA, the radius of A. And then in the other direction, going clockwise, right? The other one was positive because it's going counterclockwise. This one over B is going to be negative because it's clockwise. And we have that weight times that delta T. And so that's going to be the impulse. But we also need that moment arm. So we need to make it into an angular moment and angular impulse. And that's going to equal the angular momentum right here of the pulley. And then the contribution to the angular momentum, that the linear momentum of mass A times that RA times the moment arm that's been placed against. And then that's going counterclockwise, but also VB2 is also, the momentum is also going to result in a counterclockwise motion. So zeros over here for the before. We plug in that 25 kilograms and the acceleration of gravity, get the weight. That delta T is what we're trying to find. We get the RA, negative again here for the mass of B because it's going in the clockwise direction, but it also has that delta T and its moment arm. And then we plug in for the rest, and here are all knowns that we were able to establish up earlier, and we're able to solve for delta T. So that's the answer. But what if we wanted to check this using work and energy? It's not always possible, but in this case it is, right? So we have to be careful there. I'll discuss in the next example why work and energy is not possible, and we won't get the same answer. So I'm using the Beer-Johnston notation of having kinetic energy be T, which is silly, and potential energy is V. right? So I write that T1 is 0, V1 is all of these, okay, and I also do a weird thing where I make V1 is negative potential. It has some negative potential energy in it, right? Because what I'm doing is essentially I'm studying a datum that's like right here onto the thing, and then one goes down and another goes up, right? So in this case right here, WA is going down, so its initial potential energy is large, whereas WB, the way to B, is going upwards. So to start with, it has lower potential energy than it will later, so it ends up being negative. I never like that negative potential energy. But anyway, we go ahead and put all those things in there, and we could solve for what YA is going to be. That's what we'll find. And then we can, from this, we assume that the potential energy at the end is 0. And let's see. Okay, so we get the kinetic energy at state 2. Kinetic energy at state 2. And that's all of those things. We already knew all the velocities, so we're able to place all of them in there. And so here is the kinetic energy in Newton meters at state 2. And if we solve for that now, if we plug this back in, and I didn't even bother to do that, right? But if we write in the kinetic energy 1 plus the potential energy 1 plus the outside influence, which is going to be 0, it's going to be equal to the kinetic energy 2 plus the potential energy 2. And the way I have this set up, we start out with no kinetic energy, right? And then I made the potential energy all over here, that V1, is all over there. So I got a value that's related to the change in position. And then we do know there's no outside influence, and we do know the kinetic energy at state 2, because we know all the masses and the mass moment inertia, and we know the omega and V2, VA2, and VB2. So we have that kinetic energy, which I found right there. And then the potential energy, which is, by the way, we were playing around with the datum, it's set equal to 0. And we find that the YA is 5.304 meters. I note that that's just a crazy coincidence. What we need with the time, it doesn't matter. What we need to do in order to find time now, because we're using work and energy, we need to use kinematics, and we can use constant acceleration kinematics because none of the forces are changing with time. So the acceleration has to be constant. And we can just use that of the velocity squared equals the original velocity squared plus 2a delta y, and we're just going to apply it to this guy, right? Just to a. And so what we can find what the acceleration is going to be, 3.771 meters per second squared. And it makes sense that it's like going to be less than 9.81, right? Because it's got some resistance to its motion because of its mass. And we do that and plug him back in here, right, after we found that acceleration. And look, we get the same time, right? So what we've done here is we've shown that work and energy can be used to also solve what was set up in this problem. They are related. They're second cousins. They all came from Newton's second law. So that's today's video. The next one will show you an instance where you can't use the conservation of work and energy. I don't think I've calculated that out, but I'll leave it to you. We'll see.